Okay, welcome back to the second half of the session on gravitational waves. We now have Antoine Petitot, who is going to bring us to the realm of low frequency gravitational waves. Antoine, go ahead.
Okay, so thank you very much for the organizer to inviting me. And I will talk about space-based, moon-based, and PTA, gravitational wave observatories. So I will cover mainly LISA and PTA, but I will also talk about the other space-based project and some of the moon-based project. So here we are talking about the low-frequency gravitational wave. So all the things that are below the, let's say, the Earth. So if we want, so first we have the seismic noise on Earth, so we cannot observe this band. And moreover, you need a very large detector. We need a detector larger than 100 kilometers. So you need either to go to space or to use another technique. So for all the detectors that will be between 100 kilometers and 1 astronomical unit, we will use space. And then for very low frequency, for the nanohertz band, we will use galactic scale detector, that is pulsar timing array. I will start talking about LISA. So I guess you already know LISA, but I will recap for everybody. So LISA is Laser Interferometer Space Antenna. So we have 3 spacecraft in heliocentric orbits following the Earth. The center of the triangle is following the Earth's orbits. And the spacecraft are separated by 2.5 million kilometers. And the goal is to detect the picometer level change of distance between the spacecraft. So for that, we need 2 key techniques. First, we need to have a measurement point to be shielded from the fluctuation that we have in space and to follow only gravity. The technique that is used in LISA is to have test mass protected in the spacecraft. And so you have a test mass in the spacecraft. It's a small cube by 4 centimeters, 2 kilograms. And the cube is not touching mechanically the spacecraft, but free floating in the spacecraft. The spacecraft always measures its measurement to the cube, always measure the position of the cube, and readjust itself with microthruster to keep the cube in touch. We have 2 types of reading, so interferometric readout on the sensitive axis and capacitive sensing. And this system is extremely precise and has been successfully demonstrated by the LISA Pathfinder mission. So you can see here it's the residual acceleration. So this was the requirement for LISA Pathfinder. This is the requirement for LISA, and it's what we reached during the LISA Pathfinder mission. This was just after 40 days of mission. So it works very well, and we will use the same technique as the one that we use for LISA Pathfinder in LISA. The other big thing is we need very precise measurement between the spacecraft. So we need this picometer level precision in the measurement. So we have our 3 spacecraft. The design may be a bit different because we have some news. But, so this shape will be not probably anymore this kind of shape for the spacecraft. So we have in each spacecraft, we have 2 MOSA, 2 tubes like that are called movable optical subassembly. And in each of these MOSA, you have a telescope, an optical bench, and the mass behind that. Here, we cut the system so we can see all the elements, and you see the test mass here. And this optical bench is a quite complicated piece of zero dur. We are doing 3 we have at least 3 interferometers on each optical bench. And the 2 main interferometers on each optical bench are measuring the position of the test mass with reference to the spacecraft and the position of the spacecraft regarding the distant spacecraft. So we measure spacecraft to test mass. We measure also spacecraft to spacecraft, and we can virtually recompose test mass to test mass, and we are doing that for each arms. Then the LISA data. So the goal of the LISA data is to observe all these gravitational wave sources emitting in the milliards band. So we have our detector. We collect the phase meter measurement from the phase meter plus all the other diagnostic data. This is received at ESA. And we are doing some calibration correction, resynchronization. We are cleaning the data from the laser noise that is completely dominating the data. And we obtain 3 TDI, 3 channels, 2 are independent. And we are performing some data analysis on that to obtain the catalog of gravitational wave source. And this is performed, some part of that is performed at ESA, and a big part of that will be performed by European member state, what we call Distributed Data Processing Center, and another part will be performed at NASA Science Ground Segment. Here's the timeline of LISA. So LISA, just to remember, it's not a new project. The first proposal of LISA was more than 30 years ago. So the mission has been approved in 2017, but most important, the mission has been adopted 1 year ago in January 2024. So it means that the design is defined, and we have the budget, and we start building the instrument. Since this adoption, what happened? So ESA and the different laboratory and the different partner already start building the mission, but in parallel, they select the industrial prime, so the one that will construct the spacecraft, not the payload, but the spacecraft. And now they are finishing a co-engineering phase, and the official signature will be in June, so we will have everything settled and the final design of the spacecraft that will be public here. And then we have a long building phase. We have to build 6 MOSA, 3 spacecraft, plus all the engineering model and the qualification model. So it takes a lot of time. It seems long, but when you see the detailed schedule, it's extremely tight. And the goal, and it's still the goal, it's to launch the mission in 2035. Then we will have 1.5 years of transfer plus 4.5 years of nominal mission, plus then a possible extension to 6.5 years. And here it's where we are now. It's a big collaboration. So we have 12 European member states that signed the multilateral agreement, plus the US. And then, in addition, in the DDPC, we have 3 more countries in Europe that want to contribute. So we have more and more countries that are joining LISA, and it's the big mission of ESA. So just to show you that we are actually building things. So this is the telescope that has been built at NASA. So it's a demonstration model. This is an optical bench that has been developed in France to show that we will be able to measure the performance of the instrument on ground, because this will be done just next door at CNES. And then this is one of the pieces that we develop in my laboratory. It's a test mass simulator to simulate the motion of the test mass, and it will be installed at CNES to test the optical bench of LISA. So we are really building the thing now. And on the DDPC side, on the data analysis side, we have a distributed data processing center in place with different coordination units and doing all the things that we have to do, from simulation to production of catalog to alert, and we are developing that. We are something that 200 members today, and for example, the first common data set will be published in December this year, and we are all working on this. About the source for LISA, so LISA is covering, will observe a large number of sources. Here it's just a diagram showing the mass ratio versus the total mass. And you see that we will observe supermassive black hole binary, intermediate mass black hole binary, until wide dwarf for the equal mass. But we will observe also the very unique source of LISA that Laura already talked about, that are the extreme mass ratio in spiral. And we may also observe the intermediate mass ratio in spiral. So this is for the binary source, and we will also observe, if they exist and if they are there, the stochastic background. So stochastic background from first order phase transition, network of cosmic string. We may also observe a cosmic string burst, if they exist, and of course, it's the first time we are observing in this window, so we may have some unexpected event or source. For LISA, one of the main complexities is we have a large number of sources overlapping. Here you can see the typical number of sources that we can detect. So for the galactic binary, we can detect between 10,000 and 30,000 of detectable sources, plus we will have a background. So all the dots that you see in this diagram, in this graph, are a simulation of the galactic binaries. This is the background of the source that we cannot resolve. You have some source that we have some source that we already know. The red dot that are the verification binary. Then you have the stellar mass black hole, extreme mass ratio in spiral. So for the stellar mass black hole, it's few, between 1 to 20. For the extreme mass ratio in spiral, from 1 to 1,000, basically we don't know. But in the simulation, we are the last astrophysical estimation is more about 100 of these sources per year. And for the massive black hole binary, so it's between 10 to 100 per year. So the science objective of LISA are listed here. We are going from we are doing astrophysics with LISA, we are doing fundamental physics, and we are doing also cosmology. Yes. And if you want more details about the science of LISA, there is this document. This is the science document. This is the document describing the science of LISA that has been done for the adoption. It also gives some information about the instrument, about the data processing, but the core is really describing the science. It's called the Red Book, and you can find the document at this link. Because we are in a multi-messenger workshop, so few words about the multi-messenger. So we will have some multi-messenger with galactic interacting binaries. So it's permanent source that we will observe with LISA. We already have some source that we observe in electromagnetic counterpart, this verification binary in electromagnetic domain, the verification binary that I mentioned previously, but we will have some interaction at to understand with electromagnetic observation for this galactic binary. And in terms of transient, one of the key sources for multi-messenger is the massive black hole binaries. We may have also some bursts like cosmic string, tidal disruption. So this has to be studied and maybe some unknown. In order to perform multi-messenger with LISA, we have a low latency alert pipeline that will be designed. So it means that we will have an automatic near real-time analysis of the data when we are communicating with the spacecraft. So it means 8 hours per day. And the goal is to have the alert in less than 1 hour. And with this pipeline, that is, it's a schematic, a very simplified schematic of the pipeline here, we will detect new event, but we will also update parameter of the event that we already detected, because it's not like LIGO Virgo where the event is second. Here we are talking about events for massive black hole binary that are days or week or even months. So we will detect the event, but then we will have to update, in particular close to the merger, the sky position of this source as the data are coming. Because, for example, for some of the massive black hole binary, the error in sky shrink by a factor of 2 or 3 during the last hours. So it's very important to do that in a near real time. Now, beyond LISA, so other space, I'll say IDs, project. So the goal is to cover the two in the spectrum that I showed at the beginning. The goal is to cover the two missing bands, so the decihertz and the microhertz. For the decihertz, there was a proposal in the context of Voyage 2050. Voyage 2050, it's the future of the program at the European Space Agency. So it's between 2040 to 2060, 2070. So it's for L4, L5, L6. L4 has already been decided, but L5, L6 still to be decided. And then, so there was a proposal, the DCS observatory that will observe. You see, LISA is here, and this and ET and Cosmic Explorer are here, and this is in the middle. So it's it will observe intermediate. The science case, it's intermediate mass black hole, intermediate mass rotation spiral, and early warning for binary neutron star. Another project. So this is really like LISA, but a smaller LISA. It's an interferometer in space, but a laser interferometer. There is another project in the same band that is called AGES. So it's atomic experiment for dark matter and gravity, because it can also detect dark matter. So it uses atom interferometry. You have 2 spacecraft that are separated by 4,000 kilometers, and they are doing some atom interferometry between the spacecraft. Basically, the atom replace the test mass, and they are the reference for the gravitation, for the gravity. But before doing this kind of project in space, they first need to demonstrate that on ground. It's the project, so Ion 10 is going to be built. There is also MIGA in France that is something similar, but 100 meter. Ion 100 and Ion kilometer. And you see AGES is here. Sorry, the plot is very crowded, but it's again between ET and LISA. At microhertz, so 10 to the minus 6 to 10 to the minus 3, there is the proposal mu-RS that was again submitted in this Voyage 2050 context. So here is the sensitivity curve. So LISA is here. Mu-RS, the goal is to have a LISA of 1 AU. So you have the Earth orbit here, and then you have one LISA like that, and in the mu-RS ID, they were doing another triangle like that. There are ongoing technical study and science study, but mainly technical study that show that this triangle will be extremely expensive, extremely complicated, because this orbit is very hard to reach. So there is a version a bit reduced that is just this triangle, the blue triangle, that is called LISA Max. So it's a LISA of 1 AU with 3 spacecraft, and the orbit have been studied by ESA already, and then the sensitivity curve will be something like that. So you see that we are going at a lower frequency compared to LISA. Going to even lower frequency, to the nanohertz band, we have pulsar timing array. Pulsar timing array, what is the goal of pulsar timing array? So first, pulsar timing. The timing of pulsar, so I guess you know all what are pulsars. So it's this neutron star with a beam, and okay, on a PDF, but it doesn't work. But you should show like a lighthouse. So the beam, the electromagnetic beam will pass through the Earth, and we have very regular beam pulse that arrive. Then we observe this object, this pulsar, with radio telescope, like the Nancy radio telescope. And we have a receiver we observe in the gigahertz band. And this will be analyzed online to dedisperse the data. So when we mean dedispersion, it's the fact that the radio wave, depending on their frequencies, they are not propagating at the same speed. So you need to correct for this dispersion effect, and we are doing that online. Then you obtain the pulse, and because here the pulsar that we are observing, they are millisecond pulsars, so they are doing 100 to 1,000 rotations per second. So we have a lot of pulse that we are folding, and then we obtain a profile at the end during, for example, a few minutes to 1 hour or to few hours observation. And we compare this profile to a reference clock, and we obtain what we call the time of arrival. And one observation is 1 point currently in PTA. Which means that it takes a lot of time. But you want to detect things at the nanohertz. Nanohertz mean you want the wavelength of the gradation wave that you want to detect is the order of the year. So you are taking basically 1 point every few weeks, and then you construct your data like that, and you obtain this kind. Okay. First, so. Yes, and you have your series of TOA. But what are the ingredients and that will modify, that will impact your data? So if these TOA are not perfect, there are many effects in that. There are effects due to the pulsar itself, so the period of the pulsar, the evolution of the period, the sky position of the pulsar. We have to take that into account in the model of the TOA. There is also the pulsar environment. For example, if the pulsar is in a binary, we have something like the Shapiro effect. That is the fact that when one of the objects passes through the beam, you have a deformation. And if you don't take that into account, you will have a problem in your modeling of the TOA. We need also to take into account the proper motion of the system. And then you have the propagation of the beam through the interstellar medium with like electron cloud that are passing by, and will interfere with your radio beam. And then we also, because we also need to take into account the position of the Earth. The position of the Earth is very important for PTA, because if you have an error in the position of the Earth, as you will see later, we are searching for a correlated effect. If this error in position will be another correlated effect that could be confused with gravitational wave. And then you have gravitational wave. So we need to do a model for each pulsar. This is an example of the TOA time of arrival of one pulsar. It's one of the best pulsar that we have in the European collaboration. It's 1909 minus 3744. And then you see all these points, and we are working on all these points. And this is around 0, because here we subtract a model that takes into account all the effects except the gravitational wave that we understand in the data. And here it's all the parameters of our model. When you have a gravitational wave, you will have a modification. Without gravitational wave, our model is perfectly reproducing the pulse. And when you have a gravitational wave, you have a slight variation between what your model predicts and what you really observe. And it's how we observe the gravitational wave. So we are searching the gravitational wave in the residual. Of course, if you have only one pulsar, it's almost impossible to identify any gravitational wave, because you have all the other effects, and it's impossible to say this is due to gravitational wave or this is due to another effect at the pulsar level that I did not model correctly. But why PTA work, it's because the gravitational wave, it's a correlated effect between all pulsars. And so if you and so we are searching for a correlation between a large number of pulsars. This is the modeling of the shift in time due to the gravitational wave. And this depends on the source location, the pulsar location, and the usual characteristic strength of gravitational wave. And if it's an isotropic background, we have a very specific we have a key features that we are looking for. It's a spatial correlation called the Ellingsdown curve. So if it's an isotropic stochastic background, you expect to have this shape in the diagram, the correlation between pulsar as function of the different angular difference between pulsar. And then if we found this pattern in our data, it means that we have a good chance of detecting a gravitational wave. What are the source of gravitational wave in the nanohertz band? It's again supermassive black hole binaries, but not the same mass as the one that we were talking for LISA. For LISA, it was between 10 to the 4 to 10 to the 7, while for PTA, it's between 10 to the 7 to 10 to the 9. And we observe them far from the merger, let's say thousands of years before the merger. So we don't have, if you see here, we are sensitive, the strain that we can detect is 10 to the minus 15 compared to LISA that is 10 to the minus 21. So the sensitivity is not as good as for LISA. But so we are sensitive only to the sources that are close and to the sources that are not that not that small, so to the heavy source. We can detect individual sources or a stochastic background formed by the collective assembly of thousands of supermassive black holes. We also expect to detect, or it's a potential source, the stochastic background from cosmological origin, again, cosmic string networks or first-order phase transition, but not the same kind of first-order phase transition as for LISA. LISA, it's more electroweak. Here it's QCD. The collaboration PTA, so we have the European collaboration with 5 radio telescope, and we have the international PTA. This is a collaboration of collaborations. So we have 2 other historical collaborations, the Australian with Sparks, US, Nanograv, and Chime. And now we have 3 new collaborations that joined. It's in PTA, Indian Pulsar Timing Array with GMRT and ORT telescope, China PTA with FAST, and MERCAT in the African Pulsar Timing that joined with this very nice instrument of 64 antenna, and soon we will have the SK. So we have a worldwide collaboration now for PTA. The current result, so we have a strong evidence for a detection of gravitational wave with PTA. It has been published in 2023. This is the ePTA result. And this is the amplitude versus spectral index for for the power law of a stochastic background. And this is quite well constrained. But we don't have more information at the moment. We have 3.5 sigma detection of something as a gravitational wave signal in the ePTA data. We check that it's not a dipole, it's not a monopole, and it's really a quadrupole. So it means the curve that I showed you before, this Elling's-Down curve. We have, so here you see the Elling's-Down curve. There is some significance. The error bars are large, but there is some significance, and the base factor is something like 60 here. And the other collaboration found the same result. The 2 other collaborations, Nanograv and the Australian PPTA. And here is the comparison between the 3 collaborations that we perform at the IPTA level. Now we are joining the data to analyze everything together, to confirm the signal and to characterize it a bit more. So yes, IPTA in the near future. ePTA, the result that I showed was 25 pulsar. Now at the IPTA level, we are combining 121 pulsar. It's quite complex to combine this number of pulsar. We have to perform a fit with a very large number of parameters. So it takes some time. And the next step will be SK with more than 100 pulsar that we'll observe with very, very high precision. The first data for SK will be in 2028, and we hope to understand better this signal. Multi-messenger with PTA, it's individual supermassive black hole binaries. So they are close, EV. So in terms of the possibility of having a counterpart, we have quite good chance here, and we are already performing some targeting search using some survey like the Catalina real-time transient survey or the Swiss the ZTF catalog. Then, quickly, for the end, I will talk about what are the moon-based gravitational wave observatory. Again, it's project ideas, while LISA and PTA are very concrete. First, lunar gravitational wave antenna. It's an array of seismometer, and the idea is to use the moon as a resonant bar, like the Weber bar, and this seismometer will detect the vibration of the moon due to the gravitational wave passing by the moon. So we have here in this project, it's 3 seismometers that have to be protected from any perturbation. So they are in a crater. And you have the power station that is here. And then the goal here, it's more the desierts. You see the sensitivity curve here. And so the goal, so it's study the astrophysical explosion, exploring black hole population, measure the Hubble constant, so as for the other deserts observatory. So it's one of the projects. And there is another project called LILA, Laser Interferometer Lunar Antenna. So this project is doing 2 things, 2 ways of detecting gravitational wave. There is also the idea of having seismometer. So we have, again, vibration of the moon that will be induced by the fact that you have a gravitational wave passing by the moon. And in addition, an interferometer a la LIGO Virgo. So it's a bit more complex, but you have a free-falling test mass in this small cube with laser. And here it's one of the plan. That they have in mind. And they were, if you want to know more information, they were either about LGWA or LILA. There were 2 workshops about that end of 2024, and you can go to this website. And again, LILA, it's for observing sub-Earth gravitational wave, so early warning of BNS, type 1 supernovae, and survey of intermediate mass black hole to the dark age. It's ideas. It will be long-term project, but in terms of R&D, we need to keep an eye on that, and we need to develop this technology because the moon is a place where we expect to have more and more activity. But maybe if we have too much activity, that will perturb the detector. So we need to be careful. But okay, I reached my conclusion. I am on time. Okay, so the gravitational wave observation at the milliards and at the deserts, it's space-based and moon-based instrument. The key instrument is LISA that has been adopted and that we are building. That will do astrophysics, fundamental physics, and cosmology. But there are many other ideas, either in space or on the moon. And at the nanohertz, in the nanohertz band, we need a galactic scale detector like pulsar timing array. And we already have a strong evidence for a gravitational wave detection obtained by the 3 collaborations, EPTA, Nanograv, and PPTA. And we will have soon a confirmation, hopefully, with IPTA. And we hope a better characterization, understand if it's a stochastic background or if it's a combination of individual sources. And then we will have then SKA that will really add a lot of information in the PTA band. Thank you.
Thank you, Antoine. Any question? Okay. I had a lot of questions.
Thanks a lot, Antoine. Okay, yeah. I was wondering, you mentioned this multi-messenger link of the PTA signal, assuming it is nearby individual sources. But how good would you be able to point to the source location then with PTA, and how would you do that?
PTA is not very good at the sky localization. We need more and more pulsar to obtain a better sky localization. It's why in the IPTA, we really push to have a maximum number of pulsar. We go from 25 to 120. But still it's very large. Huh? It's under a square degree. It's more something that the fact that you can identify the counterpart will be more based on the periodicity of the signal. The targeted search, they are not really on the sky position, but they are more on the fact that there is a part that is the sky position, but the most important part is trying to find a counterpart that have the same periodicity as the one that you observe in gravitational wave. And in order to do that, you need to do survey that observe source like AGN for many years in order to have this periodic signal of years.
Yeah, just a question concerning the alerts pipeline for LISA. So my ignorance here, you say that you will be able to do that 8 hours per day, but because it's not possible to do it on the spacecraft.
No.
Because it's too heavy. I mean, in terms of computation, or.
Yes, it's too heavy in terms of computation, and we need to do some cleaning. And anyway, we are not communicating with the spacecraft during 16 hours.
Yeah,
we hope, there is a secret hope that, because in order to, the design of this 8 hours of communication per day, it's based on its track, that is the ground antenna network at ESA only. If we use the DSN, that is the Deep Space Network of NASA, we may increase the coverage and have, maybe we will be able to run the low latency alert pipeline 24/24.
Okay.
Going to show my ignorance of PTA analysis here, but first of all, congratulations on the result and the discovery of these PTA, the gravitational waves. But in terms of science yield from that, does it give you, for example, can you, from your result, your excess, can you place constraints on like the space density of supermassive black hole bodies in the local universe? And how does that compare then to estimates from electromagnetic observations?
So it will tend to push the rate of supermassive black hole binary merger to be higher than what we would expect. If you talk to, I don't know, Marta will be here this week, I guess. No. Okay, but maybe Marta Voluntary will talk about that. But they were expecting to have a lower signal for PTA, and in fact, we are detecting something that is at higher amplitude than what they were expecting. So it will mean that, for example, the delay between the merger of the two galaxies and the merger of the binary is shorter than what some of the models predict. So it already put some constraint on the population of supermassive black hole binary. And this, in addition to the last observation from James Webb, help to constrain the model. So we start to have more and more information to constrain this model.
So if you extrapolate that sort of further into distance, this presumably has impacts on the whole question of black hole growth and so on, then potentially, maybe.
Sorry?
So if you were to extrapolate that to higher redshifts, does this then potentially have implications for the whole discussion of black hole growth?
Yes.
Okay, yeah, that's cool.
Okay, we have some time for another question.
Right, going back to this previous question on multi-messenger with PTA sources. So you said that you currently are looking for correlations with, for instance, ZTF sources. Did you say you're going via catalogs, or are you doing specific new searches?
At the moment, it's using catalog, but there are some investigation. For example, Vincent is doing some investigation using specific observation and dedicated on specific source. So we start with catalog because it's what we have, and then we are doing more and more specific investigation using maybe sometimes targeted specific observation also on ground to confirm if it's if the periodicity of the source is what we see. So we have candidates via the catalog, I would say, and then we confirm this candidate and we search in PTA. Maybe Vincent or Nathalie, you want to add on that?
Yeah, that's what. Yeah.
You will talk next week about that.
Yeah, I will give a talk later this week. Wednesday.
Any other question?
And about PTA, I think Katarina will give also more information on that Thursday, correct? Yeah.
Well, if there is no other question, I will make my question since 2 years.